We want to show that 3 plus 4i is a 0 of f of z is z cubed minus 7z squared plus 31z take away 25. In other words, we want to work out f of 3 plus 4i. So that's going to be 3 plus 4i cubed, take away 7 times 3 plus 4i squared, plus 31 times 3 plus 4i, take away 25. To save time, I've actually worked out 3 plus 4i cubed and 3 plus 4i squared on my class pad. So we get negative 117 plus 44i, take away 7 times negative 7 plus 24i, plus 31 times 3 plus 4i, take away 25. So if we gather up all of the real parts, we get negative 117 plus 49 plus 93 take away 25. And if we gather up all the imaginary parts, we get 44 take away 168 plus 124. And that is indeed 0. We're asked to state another 0 of f of z, and hence show that z squared minus 6x plus 25 is a factor of f of z. Well, another 0 must be 3 minus 4i, given what we know about complex zeros occurring in conjugate pairs when all of the coefficients are real numbers. That means that z minus 3 plus 4i must be a factor, and so must z minus 3 minus 4i. And therefore the product of those two things must also be a factor. If we expand this out, we get z squared, and then when you do this multiplication and this multiplication, you'll find that you get negative 6z because the imaginary parts will just cancel out. Finally, when we do this, we're getting 3 plus 4i times 3 minus 4i, difference of two squares, so that's 9 take away 16i squared, which is 9 plus 16. So we get plus 25. Hence we want to solve f of z equal to 0. Well, f of z, so what we're solving is z cubed minus 7z squared plus 31z take away 25. That's going to be equal to some linear factor multiplied by this quadratic factor. Now, to get a single z cubed here, this linear factor must start with just z. We've got negative 25 here and positive 25 here, so we must need minus 1. And so we know fully factorized this is z minus 1, z minus 3 plus 4i, and z minus 3 minus 4i. So if we're solving that equal to 0, we get z equals 1 and 3 plus or minus 4i.